welcome to the second day of the workshop. And our first speaker is Yair Hartman. And this is the important one, about groups with bounded harmonic functions. Yes.
Okay. Thank you. I'm going to talk about which groups have bounded harmonic functions. A joint work with Josh Fish, Omer Tamuz, and Puya Vaidi Ferdowsi, three of them from Caltech. I was sitting on my sofa the other day, and I thought to myself, how can anyone not like bounded harmonic functions? Right? But then I realized that maybe I should introduce some of it. So I'll start with describing what bounded harmonic functions are used for in this context. Then I'll sketch some of the history, what is known, and I'm going to give you show the construction, what we are doing in this work. Okay, so I'll start with the beginning. So the class of groups that I want to consider are infinite groups, and I want to think of a notion of compactifying these groups. So not exactly compactifying maybe, but to give a description of the boundary of the group. One way to go is to add another point, so to build the one-point compactification, but it doesn't tell you much about the group somehow. And I want to think about a situation where you can build more interesting or a richer object than one point as a compactification for the group. And in this work, exactly what we're doing is characterizing those groups for which you cannot have more than the 1 point interesting compactification. Now I just need to say, what do I mean by interesting, right? Okay, so in general, how you construct a boundary. So you have an object, and we want to think about the boundary of the object in some way, but we don't know how does it look. So we can take a look in a classical way when we have an object that we do know how its boundary looks like. So this is D, maybe the open unit disk. And we do know what's the boundary of this shape. B, the boundary here would be the circle. But how can we tell other than staring at the board, right? Maybe I want to have an intrinsic explanation or description of the boundary in terms of the object itself. So this is the question that Dirichlet asked, right? Given so you have a body, some body, and Dirichlet can give you the temperature of the body on the boundary of the body, and you need to complete and to tell me what is the temperature at each point in the interior of the body. So this is the question. What is the property that we so say that we have a function f? It's a function on the boundary. It's the temperature function. Say it's to r. So then we need to say, okay. So the model here. So you give me the temperature outside, and I need to tell you what's the temperature inside. What is the property of the temperature that is important for me is that the temperature at a point would be the temperature around. It will be the average temperature of the points around it. So it will satisfy the mean value property. And the solution to this Dirichlet problem is all this, of course, well known. His student Poisson gave the description how, given a function here, you can describe the values here. So you can do it in the following way. I know that it's all very classical, but I want to take something out of it to general setup. So you take a point x here, and what you can do, you can start to perturb it around and around until it hits the boundary. And by that, you can produce a function. You associate with each element x, you can associate a measure, nu x, a heating measure. It's a probability measure on the boundary, which is the way that the first heat distributed here. Okay, and then Poisson transform is the following. So given a function f, you can define h, a function here, to be, you just integrate the function, the boundary function, according to the heating measure from this point. So if you start very close to here, you probably want to take into consideration mostly the temperature here rather than the values here. Okay, so what we gave here is a way to associate L infinity functions on the boundary with bounded harmonic functions, I'll denote it that way, on the disk itself. And although it's very classical and we all know it, and it's very nice identification, I don't want to get into too many details here, but there is a beautiful takeout from this story so far. And it is that using harmonic functions, you can reveal the structure of the boundary. Harmonic functions are functions on the object itself. They don't know somehow what's the boundary, but they still can recover in some way. And this is a and this is the takeout that I want to take. The idea would be in a minute to use groups for groups that we don't know how the boundary should look like, and to use this abstract idea. Before leaving the classical setup, let's recall the Liouville theorem that states that that there are no bounded harmonic functions on the whole plane, only the constant functions, which I want to think here. If this is a one-dimensional space, so it means that the boundary is one point. So somehow you need to take the complex plane and to think about it that it has only one point as its boundary. Okay. Now, as I said, I want to move to groups. And while in the complex situation, I had a very clear notion of neighborhood, for groups it is less obvious what do you want to do. And for that, we will discuss, we use a measure, a measure on the group or measured group in order to describe what do we mean by the mean value property. Okay, so this is so this will be the setup of this talk. So gamma will be countable discrete group. What is going on? Group. And then we'll take, I'll denote by mu always, a probability measure on the group, which is generating. What do I mean by generating? It means that if you take the support of the measure, and not only the support of the measure, but all its nth convolutions, you see the whole group. Okay, so in other words, the semigroup generated by the support of the measure is the whole group. So this would be generating for me, and then given that we define a function. I want to define what harmonic function. So a function, not f, it's h, from gamma to r, say, is mu harmonic if it satisfies the mean value property according to what mu the way that mu see the group. So if H of G is the sum of H, it's the sum of H G gamma in mu of gamma, where gamma runs over the elements of the group. Okay, so somehow if these are the neighbors according to mu and with these weights, this is bounded harmonic functions. These are harmonic functions, and I want to denote again by a fancy H gamma and mu, all bounded harmonic functions, mu harmonic functions. Functions on gamma. Okay. So just very similar to what we had here with the Dirichlet and Poisson. Here, this is a theorem by or a theory actually that was developed by Furstenberg. Late 60s, beginning of the 70s, depends which exactly. Okay. Given a pair gamma and mu, there exists a standard probability space. Okay, where I should put the gamma? A gamma standard probability space that I denote by pi of gamma mu, called the Furstenberg Poisson boundary, which in a similar way to here describes the harmonic function inside, or such that the bounded functions on this boundary is in one-to-one and more than one-to-one correspondence, nice correspondence with the structure of the bounded harmonic functions on the group. And again, for me, the nice thing in this identification is that these are functions on the group itself. I don't need to know the group, what's the boundary at all. I can discuss intrinsic functions and to reveal somehow what is going on outside. And just as the Poisson Transform that gave us the way to associate boundary functions with bounded harmonic functions, this is given by the same. Here also we have a stochastic process, which is the random walk, the mu random walk on the group. I don't know how deep should I get into it, but okay. So that is that for me, and then borrowing from this result, we defined a pair. Gamma mu is Liouville if, okay, one way to go is to say that the bounded harmonic functions are only the constant, but I want to think more, I mean, the way that I like to think about this object is more that the Furstenberg-Poisson boundary is being trivial. This is the one-point compactification that I promised, although it's not exactly a compactification. This is a measure space, but just if you know the object, so you don't need what I'm saying now, And if you don't know the object, so it is more helpful to think about it as first approximation as a compact space. It's not, but okay. So 2 examples. That will motivate the discussion. So first is a simple random walk on Z. So we have the classical process, and we can ask ourselves, what does it mean that a function on Z is harmonic with respect to the simple random walk? I mean here mu of 1 equals mu of -1, right? Is the it's enough, but also equals half. And it's easy to see that, okay, in that case, you really get that these are just arithmetic progressions, and the only arithmetic progressions which are bounded also are the constant. So this is an example of a pair group with a random walk, which is Liouville. Now you might say, okay, it's clear because this is recurrent and it's somehow very too obvious example, but it's not about that actually. For the group Z, or the group Z cubed if you wish, whatever measure you're going to put, you're going to get this phenomena. And I'll discuss it further. But luckily, it's not always the case that all the groups in the world are Liouville, and this is why we can say something. So the other motivating example is the simple random walk on the free group, and we already saw it, some of it in Gabor's talk. So simple random walk here, just mu means that mu of A is mu of A inverse mu of B inverse equals quarter. So this is really the simple random walk on this graph, if you forget about the fact that it's a group. And in that case, it's good to think of the boundaries being attached here, although it's a measure on these ends, the space of ends. And the way to see that it is not Liouville, the way to find a bounded harmonic function, is to think of a temperature outside. So you take this one, maybe this area, all the words that start, the infinite word that start with A, and you let here the temperature to be 1 here, and here it's 0. And then the bounded harmonic functions that you get out of it is actually at each point you assign the number that you're going to assign is the probability that it will end its life in this branch. Okay? It's much easier to think of the temperature 0, 1 when you talk in Celsius. It's more relevant. Okay. So there are groups with the bounded harmonic functions, with bounded harmonic functions, there are groups without, and the question is why? Okay, this is the first question that I want to ask. What's the difference between these two groups? Okay, it's a lot of differences, but what is the deep thing? What I'm going to claim that it's not the growth or things like that maybe you have in mind now, but the commutativity. So I want to claim that in a deeper, in some higher level of commutativity, this is the problem of Z, that it cannot support bounded harmonic functions, and the free group is really not. So we will see. So yeah. What? Here? So what are the quantifiers on the measures? So two natural questions are arising here once you have this definition. One is, what are the groups that, for any random walk, the Poisson boundary will be non-trivial? The other natural question is, what are those groups that such that for any random walk it will be trivial? And this is exactly the two levels that I want to discuss. Maybe I'll start with the, okay? So, yeah, we're going to completely characterize classify what is going on here, so we will see exactly what is going on. So the first class of groups that, so this is a theorem, I guess that it's by Furstenberg, that any random walk, any mu, always generating. I never talk about non-generating measures. Any generating measure on a non-amenable group is not Liouville.
I apologize.
Yeah.
When you say measure, you mean symmetric or?
No, I didn't say symmetric. All of what we're going to say will work for symmetric, but just for this level of representation, it's not important. Okay, non-amenable groups always for any random walks that you will pick. So for the free group, I don't care which kind of random walk you want to pick, you're going to find non-constant bounded harmonic functions. And then he asks what is the other, whether the other direction is true or not. And this was proven by Kajmanovic and Vershik. And by Rosenblatt in the early 80s. The other way is also true. Any amenable group admits a measure mu, a measure which is not, which is Liouville. And if you think about it, I want to spend 1 minute, or I don't know, some part. No, on what is the task, what's the goal in proving such a theorem. So you take, you have an amenable group, so you have a sequence of almost invariant measures on the group. And the goal is somehow to centralize, no, not centralize, but in some way to find a single measure such that its own convolution powers will become almost invariant. So this is the somehow the problem here. The measures to begin with were unrelated to each other, and somehow you want to find one such that its own convolution powers are doing the job. So this is completely classified this kind of groups. It's exactly amenability. And then the question that that I want to ask is for the other side. So the question now, for which groups the Poisson boundary is trivial for any mu. Again, generating. Okay. Are there at all? Okay. So yes, there are. And this one, okay. So it's a term. Okay. Let me say first. These groups are called Choquet-Denis. Choquet-Denis groups in the literature for the following reason. I'm not sure that I have a good explanation why. Okay. For the following reason, theorem. So it was first proven by Blackwell in 55, sorry, and 61 is the Choquet-Denis. And Choquet, okay, I'll write Choquet Denis. It will promise that I have less spelling mistakes. In 61, that abelian groups are Choquet Denis. So on abelian groups, you'll find no bounded harmonic functions regardless the measure. And it's really regardless the measure, and the groups doesn't have to be finitely generated. So it's a very soft argument about commutativity. Blackwell wrote it in a bit different language, but essentially what he's doing is ZD that he's considering, but the argument is essentially works for any abelian groups. So Choquet Denis. By the way, this is before the object of the Poisson boundary was defined at all. So this is just asking what are bounded harmonic functions on the group without having any geometric picture in mind. The next step, can we go above abelian? So the answer is yes. And this is Dinkin Malyutov. They prove it in whoa. What did they do? This was in 60, and this is in 61. But a well-known, a better-known proof is the one given by Margulis, which is a very elegant proof given in 66 for the same result that that nilpotent groups are Choquet Denis. Once you have a good, nice proof for that, you can do it in a relative way to claim it for the center, and then use induction to prove that nilpotent groups are Choquet Denis. And the reason that I left here space is that you can do virtually. Finite index doesn't matter for this kind of discussion. So virtually nilpotent, if you have a nilpotent group of finite index, it means that you're going to see no bounded harmonic functions for any random walks that you will pick. Okay.
This proof works for non-finitely generated groups as well?
Yeah. What? The virtual? What kind? Choquet Denis?
Nilpotent groups, non-finitely generated nilpotent groups.
Yeah.
Choquet Denis,
Yeah.
or even the non-finitely generated case?
Yeah. Even more. Okay. I'll say what's more. Okay, questions, by the way? Comments? Okay. So then what do we have? So, okay, and then in 83, the paper by Kajmanovic and Vershik introduced the idea of discussing the triviality of the boundary in terms of entropy theory, and then it follows, they show that if you have a sub-exponential growth groups for finitely supported measures, you'll find no bounded harmonic functions for the reason that there is not enough room to produce entropy. So it's too small somehow. To Aver. Okay. Okay, thank you. But anyway, this is a discussion about finitely supported. In that case, finitely supported or symmetric, this is where you start to discuss other things. But then they asked, conjectured, Kajmanovic-Vershik conjecture that groups of exponential growth are not Choquet Denis, and here you must consider, if you want symmetric measures, you must consider non-finitely supported measures. So they ask whether groups of exponential growth are Shokedeni. And yeah. So if you do symmetric random walk, and you can think of the lamplighter on Z. So that's the example that rules out the possibility. Which every symmetric finitely supported random walk will give you a trivial boundary, but there are other measures with non-boundary. Symmetric and not finitely supported. Okay. Yeah. So this was in '83. In '05, Anna Erschler in '04, she showed. So I'm not doing. Okay. She showed that for solvable finitely generated groups, Shokedeni is actually equivalent to virtually nilpotent. So within the class of solvable groups, we have this classification, and then also, and she, okay. There are also relevant results around it, but I don't want to get into all the history in order to show something about the present. Okay, and then what I want to describe, I mean, our work. We show the following. So this is again a joint work with Josh Frisch, Omer Tamuz, here, Omer Tamuz, and Puya Vahidi Ferdowsi. So we show that for finitely generated groups, Shokedeni is equivalent to virtually nilpotent. So we completed there. So if, let's say, for finitely generated groups to begin with, if amenability is this threshold where you always get bounded harmonic functions, virtually nilpotent is the threshold of being too small to support any random walk with non-trivial boundary. So we are not really dealing with virtually nilpotent. I'm misleading you on purpose. Not on purpose, because this is more somehow the class of groups that people used to think about, and I'll say exactly what is the precise class of groups which are Shokedeni within the discrete countable groups. Okay, so
the statement you wrote on the board is literally correct or literally incorrect? You're misleading us, but how far?
I'm just showing you what is the result for finitely generated, but I have some general result that this will follow.
So the condition that you have is for finitely generated groups, it's equivalent to virtual nilpotence, and in general, it's
Yeah, in general, it's something else. You need to say something else. Yeah.
Going back to my previous question, sorry. So Margulis and also what you're going to talk about in general is for discrete groups.
Right.
Okay. Not for
Locally, it works also. I don't. It's not. I don't think that it's about. I don't. It's not about.
I didn't ask me this question for continuous groups. Not so long ago. So
Okay.
He doesn't know what
I don't want to say. I mean, I don't want to say. I doubt. Yeah.
I don't want to bother you now, but there's so many buttons.
Yeah.
There is a natural, not finitely generated, which is like locally nilpotent. Can you say something about them?
Yeah. So
Finitely generated nilpotent, but not bounded on the.
this is exactly the classes that this is exactly, yeah. So okay. So yeah. So what do I want to do now? Okay. So what do I want to do now? So okay. So first, okay, it solves the this conjecture because we know about exponential growth groups that they are not virtually nilpotent. But what I want to do is to show you now the proof or how the right. Eventually, what do we need to do? Given a group, to find some measure with non-trivial bounded harmonic functions. So I want to show you the construction. So I have 3 parts from now on. I want to discuss what ICC, which is ICC groups, which will enable. I'll be able to discuss the correct statement here, or the more general statement. Then I'll mention 2 easy lemmas for random walk theory and ICC, and then I'll show you the construction. So what do I mean by ICC? Here's the definition. So gamma, a discrete countable group gamma, has the ICC property, infinite conjugacy class, if every non-trivial element has infinite conjugacy class. Okay. So this is the strong or the deep negation of abelian, of commutativity. If in the case of commutative groups, the conjugacy class is a singleton. If you are virtually abelian, so you will be bounded. Somehow you will have a finite orbit. Here, having an infinite orbit for the conjugation action on each element, this is a strong. This is what I want to convince you that this is the correct strong negation of the abelian phenomena. What is the story about these groups? So you have a group, and this group really wants to be ICC. But what bothers is that you might have elements with finite conjugacy class. Okay, but all of those elements, they form a normal subgroup. So you mod out by that, and the group almost happy. But then it realizes that might be some elements that had infinite conjugacy class, but after you mod out, now they have only finite. So you need to keep on modding out more and more a larger and larger normal subgroups like that. And it won't be even enough to do it only finitely many steps. You need to do a transfinite process here. But all in all, any group, any discrete group, not finitely generated, has a normal subgroup, which is called the hyper FC center. And once you mod out by this hyper FC center, you get an ICC. Okay, this ICC might be the trivial group. It might be that you killed all the elements in this process. So this is exactly the distinguish. Either you have a quotient which is ICC, or you are hyper FC central. Now I just want to mention to point out that it's not important for this discussion if you have a quotient group which is not Choquet-Denis, so you are probably not Choquet-Denis yourself. Okay, it's enough to show that for a quotient group. So, yeah, no, not probably yeah. It's definitely not true because you can pull back a measure. So really, what is important? I mean, the deep thing is what I just said is a reduction to the following. So this is the proposition that we really prove that any ICC is not Shukadeni. Okay, now within the class of finitely generated group, being hyper FC central, hyper FC central coincide with being virtually nilpotent. So maybe I should say being hyper FC central, meaning that in this transfinite induction you kill all the element. It is here's an example. You take nilpotent groups of infinitely many virtual nilpotent groups with nilpotency degree going up and up. So this is not
Exponent 4, yes.
What?
Exponent 4. The more generators you have, the higher the class gets.
Okay. And then you get a group which is not finally generated. It's not virtually nilpotent because you don't have a finite degree, but for any way that you want to think about it, it should be virtually nilpotent. What it is hyper FC central. So this is somehow what I want to claim, that this is the thing. And And by the way, the fact that within finitely generated groups, virtually nilpotent is equivalent to being hyper FC central is quite old. It's from 56, sorry. By McLean. So these are all old stuff. So this is really what we are proving, and I think that I said here. So if you drop here the finitely generated, what you want to say here, if and only if you are hyper FC central. So this is now there. Okay. Okay, so what do I need to do? I need to construct a random walk and to tell you that it has bounded harmonic functions which are not constant. So this is the lemma that I promised from random walk entropy, from random walk theory. So this is the lemma. If you have a lazy random walk, so it has a positive probability to stay where it is, and there exists some k, little k is an element in my group for now, such that the lim inf of the total variation between mu to the n and k mu to the n, this is positive, then yeah. It's
an honest limit.
Okay.
Then it's a claim, not a condition.
No. Okay. Okay. This is no. Okay.
It's monotone.
Oh. Okay. Thank you. Then the Poisson boundary is non-trivial. But in words, what is written here, that if you can distinguish between the random walk that starts from the region and the one that starts from another element, if you can distinguish in the future, you can always distinguish between them, so you better have boundary events, so the Poisson boundary is not trivial. So exactly the opposite direction from Kaymanovich-Rosenblatt proof, what we need to do here is, instead of finding a random walk whose own convolution powers become more and more invariant, we need to keep them always being not invariant. The best case scenario would be if I can make this one and this one, this is in total variation norm. So if I can take and let them be in disjoint supports, okay, that would be great. I cannot do it. It's too optimistic, but up to some small probability events, this is exactly what we are doing. What is the property of ICC that I need? So this is a very cool thing, in my opinion. So let be an ICC. So for any B finite set in the group gamma, there exists an element, I want to denote by G, such that by conjugation, I just want to, you take it far from itself. Okay, I want to write here that that by conjugation you take a finite set and you conjugate it, and I want it to be totally in a different, to have a trivial intersection. I cannot make it because it might be that B consists the identity, and this is exactly what I want to say, that this is a subset of the identity, or maybe identity and maybe they're really disjoint. So this is a very nice, I want to convince you that it's very nice property. Actually, moreover, there are infinitely many such G's. So it's not like a unique one, but for any finite set, there are infinitely many elements that I want to call them. Okay, so I want to tell you. Here's the picture. There's a picture behind it. So I want to, of course, you can guess that I wanted to take B to be a ball. So now I think about maybe finitely generated group, and I'm picking a left invariant metric, and I'm thinking about the ball of radius R. And now what happens if I'm multiplying this ball from the left? Okay, it's a left invariant metric, so I guess that the ball will move just aside. What will happen if I'll hit it from the right? Okay, if the group is abelian, nothing much, but what?
Not going to stay a ball as a rule.
Right. So in a abelian group, it stays a ball, and here it is the complete opposite of that. This is part of my propaganda that I'm trying to sell here. So let's check what is the distance. So let's take two elements here, B1 and B2, and let's check just what's the distance between B1 after being hit by G, by this G, and B2. So this is the norm of G inverse B2 inverse B1G. So this is an expression of this form, and thus it is far from, thus it's not in the ball of radius R, this element. Okay, I'm a bit, there is a constant 2 here, but ignore that, which means that after you take a ball of radius R and you hit it from the right, what will happen is explosion. Each element will be a singleton now, and the distances is at least R. So everything becomes more and more apart. And this is exactly the phenomena that you want to use in order to do such a thing. Imagine that the random walk with a huge probability will explode the possible positions up to here. Okay, so what will happen? You'll start from E or start from K. At the beginning, they had a distance 8 to begin with, but at some point, this ball of radius 8 will be exploded, and then they will be far away. And then, but they're also in the ball of radius 100. So, and this will be exploded. So points will become more and more. Will go to different directions, which should give you the intuition that this is at least what we need to do. Yeah.
I don't understand the claim, so I see why it can be very far because
because this is an element. This is an element in B, right? If you want this one to have a small norm, so it should be in B.
So if the intersection.
Yeah. I'm talking about this element. So these elements, we call them switching elements. This is not the best name, maybe. Exploding elements are better names for them, because geometrically this is what's going on. Again, we are talking not about only finitely generated groups, and maybe, okay, but for the intuition, I think that this gives you some a nice integer. Okay, so now what do I want to do? I want to prove the proposition. So proof, simplified version of the main proof. So let gamma be an ICC. I need to construct mu, so I need to give you a probability measure on the group. How am I going to do that? I'm going to pick some probability P, a probability measure on the natural numbers, and I'm going to list elements in the group, G1, G2, and so on. And eventually the measure mu would be, the measure of Gm would be P of its index. Okay, so I'm going to choose elements in the group, and which element of the group I'm going to choose according to the probability on the natural numbers. Okay, let's put aside what is this P, and I'm going to tell you how do I want to list the elements in the group. Okay, so the beginning doesn't matter. I'll choose the elements by induction. So given the list G1 up to Gm minus 1, I already picked them. We choose no, we define first. Let's define. We define a set B, Bm minus 1, to be the following set. So it's K. So remember, oh, I just erased it. What I want to say, I want to take gamma to be an ICC and pick some element K. Okay, don't take the trivial element, but any other element. I want to make this element to have the property from the lemma before. So the work from K and the work from E are going to be distinguished. Okay, so I'm going to pick here K and then G1 to plus minus 1 up to Gm minus 1. So this is the set of all the plus or minuses elements that I already chose, and additionally K.
I assume you wanted to put plus minus on all of them.
Thank you. And then what I'm going to do, I'm going to pick, let me do it like this. And now, and let Gm be such that, so I want it to be Gm to explode the ball. Okay, one?
It's not a ball.
It's not a ball, but okay. Yeah, you can even enlarge it, and yet it will. So I want to take Bm to the minus 1, and then here, just for the fun, let me do 4m minus 1. It will be just safer. Maybe 2 can work, but fine. So let me write and then say. So I want this one. So I'm thinking about this set, and I wrote it in the same form. I want to have an exploding element for what? For this set to the power. So you take all the words of length 4m, more or less, in the letters that you chose until now. You get a huge set, finite huge set, and then you can find such an element. And also there's one thing that I want to do, and I want to do it also such that this Gm won't belong to this set. And again, it's possible because there are infinitely many such. Let me just say, yeah. Okay, it is possible due to the fact that you have infinitely many such, and it's not like in a, okay. Good. Why do I want to do all of this? Because now if I have a list of natural numbers, they correspond to, I can think of them as a walk. So now I want to discuss, okay, just follow me. So let S1 up to Sn and T1 up to Tn be natural numbers. So it's a sequence of natural numbers with the following property, such that the maximum between the SI's is exactly the maximum among the TI's. It's the number m, and this m is greater than n. So it's a sequence maybe of 100 natural numbers. The maximum in here is 200, say, and here is also 200, and I want the maximum, and the max and gm, this, oh, not gm, and the number m appears once in each sequence. Okay, so I have a unique maximum here for, it happened to be that they are the same, and this maximum is larger than the length of this sequence. Okay, now a sequence of natural numbers correspond to, according to this construction, to a walk, to a sequence of using this enumeration. So what I want to claim is that if you think about k gs1, it's a long sequence, gsn, I want to claim that it is different than gt1 up to gtn. Because this is a sequence of natural numbers corresponding an element, and this element and this, what? Okay, good. So I want to claim that in general, usually they will be different. Why? What's the idea? And this is so I have here the unique maximum gm. It appears here and it appears here, right? This is the unique maximum, and m is larger than n. And let me denote this thing. Okay, by b1, the leftover by b2. Here is C1, and here is C2. And if they are the same, okay, what does it mean? I can move things around, right? So I left with K B1 GM. And what do I need to do? I want to multiply by here, GM to the inverse equals C. It's C2 and then B2 inverse. Okay, this is just the same, but what's the point? The point is that this set, this element, the sequence of all, I mean, if you run over all the possibilities, they're always from this set, and hence, with the way that we chose GM, we'll say that it doesn't happen. It might happen only in the case that this is E, which means that this and these are the same elements, but this don't bother with small things. Okay? So what do I need to do? What I want to do? Now I told you the whole enumeration. It's not enumeration, but the whole list. Now I just need to say what is P. P should be such that if you draw a long sequence from this P, you're going to see a unique maximum in this sequence. That's all. Okay? And these are heavy-tailed measures. There are such. So P of n, for example, so you can just pick P of n to be n to the, okay, the right, yeah, to some n to the minus alpha between 1 and 2, it will work. Okay, you just take without a heavy-tailed probability, so each time you expect to see something so huge, and each time that you pick something so huge, it means that you're exploding what happened so far, and it's exactly how it works.
Obviously, you need to normalize if you really want it to be a probability, and that's not important.
I don't see this C here. Okay, so that's the end. You can do it from what I described here. It's not clear why it is generating. It's not generating. Why it is symmetric. It's not just symmetric, but you can do it in a generating symmetric way, and it will have finite entropy, but not any moment. I don't know that you can do it. So, so you can find a symmetric generating measure for any non-hyper FC central group, which is yeah. I didn't.
When you take two independent samples of the sequences, the two maxima are equal.
Oh, this was the worst case. In general, what will happen is that the maximum here will be much larger than the maximum here, and then we are even better because of this expression. So this is only for the case that they happen to be the same still. Yeah.
If we stick to finitely generated groups, and then the theorem says that non-virtual unipotent is mu blah blah blah. Can you find such a finitely supported?
So opening this question about finitely supported, it's a whole different world. Okay, not only that, I mean, a lot of questions in this side.
It's not known, or it's not true if you will stick to that.
That what? That any. So the lamplighter, if you stick to symmetric, okay, symmetric measures with finitely supported symmetric measures, so it's not this class of groups. It's not the hyper FC central.
But I don't understand. But if you take finitely supported but not symmetric, can we
Sub-exponential groups are too small.
What?
Sub-exponential groups.
No, but without symmetric.
That is something that's
Right. Yeah.
what did you say?
Yeah. Thank you.
Sub-exponential.
Exponential growth. All. Yeah.
Are there any other questions for Yair? Okay, so it's time to
Thank you.
hear.